For a 2D simulation of a CD nozzle, you're going to first open up the workbench and create a Fluent tab. And to start, you're going to need a geometry. I decided to create mine in SolidWorks because that's what I'm familiar with. So here's the dimensions. And then after you have your sketch, you're going to need to create a planar surface so it's able to be used in Fluent. After you create your surface, you're going to save it as a step AP214 file so it can be opened. I've already done that. And then you right click and edit geometry. I use Design Modeler. So it opens up and you're able to work on it. After that's done, you need to make sure the analysis type change from 3D to 2D. After that, you need to start the meshing. Once you have the mesh opened, I like to create the names parts. So you hit the edge tool and then start naming the inlet, the outlet, and then the walls. For the mesh itself, I usually I like to use the triangles method, but you could use the quadrilateral as well. I set the mesh size of the triangles to 0.2 centimeters. So it's a good size mesh. And then inflation along the edges for the first layer, the thickness of 0.05 centimeters with a 4 layers maximum. With that, you're able to have this part up here. After your mesh is done, you will go to the setup. Just change this to, since we're dealing with compressible flows, you need to change the solver type to density based. Once you have that to density based, you go over to the models, turn energy equation on, and change the flow type to inviscid. Next, materials, fluid, air. You change it from a constant to an ideal gas. Then create. Next, you go to boundary conditions. Change the inlet from a velocity inlet to a pressure inlet. And then for this, I use the gauge hold pressure as 5 million pascals and supersonic as 4.5 million. The thermal I set as a 3000 Kelvin. The outlet, the outlet I used 2.5 million pascals. So this will be able to get a shock inside the nozzle with a backflow temperature of 2500 Kelvin. Also set this from total pressure to static pressure. Change the operating conditions, so 0 pascals, gravity on 0, everything to 0. So the reference values compute from inlet, and then the nozzle, it's all that stuff. And then residuals, change the residuals to 1 to -6. After you set the reference values and initialize, you can run the calculation. I used 2500 iterations to calculate it, and after it's done calculating, you will create a contour under graphics. Static pressure contour. So see the highest static pressure here, a little cross right there, and then here's the shockwave. After the shockwave, the static pressure increases from here. Temperature increases at the shockwave. The density increases. Velocity decreases. And you have the Mach number. After the flow goes to the nozzle, or through the throat, it's at Mach 1 here. After it increases, it gets the shock and then decreases to below Mach 1. Properties, speed of sound, and all that. And then you have the center line. You get to create the center line by going to domain, create surface, and then line, then set the endpoints that goes through geometry. Here's the Mach number, velocity, static pressure, density, temperature, and speed of sound.